verdadeiro organizador disso aqui, que é o Alexei, que está escondido. Oi, Alexei. Isso é um assunto muito cansativo, e, portanto, eu vou precisar da ajuda de várias pessoas para responder a essa questão. Então, vou pedir, por favor, para aqui Edson, Sérgio, Luiz, Amauri e Ismael. Venham para cá, por favor. Acho que vai ter que sentar ali mesmo. Bom, esse projeto começou há uns quase 30 anos e continua andando. O que significa que não é tão fácil responder essa pergunta para quê? Como é que faz para andar uma página? Pega isso aqui.
Não, não é.
É isso? Bom, isso aí é se vocês conseguirem ler isso tudo, vocês podem dormir, porque está aqui o que eu vou falar. Tá? Eu vou falar um pouco de uma lei de conservação, sistemas, necessidade de teoria, etc, etc, etc. Em geral, depois de escrito, eu não preciso mais. Bom, o que é uma lei hiperbólica de conservação? A mais simples que a gente aprende é essa aqui em cima. Você tem uma derivada em relação ao tempo, mais uma constante derivada em relação ao espaço, em relação igual a zero. Isso aí representa ondas que andam com velocidade A. Ok? Bom, o caso mais simples, esse A é constante, é o que eu acabei de falar, mas isso aí representa muito poucas coisas. Você pode imediatamente colocar outros termos para modelar dispersão, e isso aí... That's to train your Portuguese. Sorry. Okay, I have to repeat the jokes. So I'm saying that if you succeed in reading this, you can fall asleep, because that's it I'm talking about. So single conservation law is the one, equation 1. It represents a wave or waves moving with speed a without changing shape. And that's very simple, and it's in initial chapters of our books. Now, if you add the third derivative term, you move the page, because you get dispersion, and this is an enormous field of hydrodynamics. And my colleague, André Narbin, works on hydrodynamics. If you put, instead of third derivative, you put second derivative, you get the diffusion term. And that's groundwater flow, if you want an application. And that's what was groundwater flow. Of course, this is just a beginning, the first lecture. But instead of doing this, you complicate this system by two ways. First of all, instead of having a single variable, W, you have several of them. So you have a system. And first is that. The second is that instead of A of W, which is the simplest linear function that you can think of, you put a nonlinear one. Well, so you also have diffusion, that's good, but F is nonlinear. So what this happens is what happens is that there will be shocks and complexity. And that's why I like it. Okay. So what's a Riemann problem? A Riemann problem is a problem of the initial, you can think of it as initial value problem with discontinuity. The data is constant to the left and right of discontinuity. Well, if you look at the symmetries of the problem, you'll end up seeing that there are two typical kinds of waves, rarefaction waves on the right, and shock waves on the left. The shock waves are discontinuous. The other ones are smooth. And but actually, in a system of conservation laws, you'll have not a single wave. You'll have several waves. And so what happens if you have diffusive terms is that the shocks become traveling waves. And we'll talk a little bit about traveling waves soon. So this is a traveling wave system originating from the diffusive equation that was in the previous page. And because of this, bifurcation of ordinary differential equations becomes important. Let me see if I can go ahead. So because of all these complications, what we did since I have the reaction that if I don't know something, I try to make experiments. The only way to make experiments in math is scientific computing. So starting in 1989, we started developing an interactive computer program with the purpose of finding new theory. When we understood something, besides writing paper, we also upgraded the computer program to include whatever we learned. And then we start again. Use the interactive computer program to just find new facts. This has been going on almost 30 years. The program, including inactive parts of the program, is 300 lines long. And of course, there is a team of people who help me, and without which it would be impossible. One important point about this program is that this is not a simulator. It implements the theory and the formulas from the theory. So if you try to use it as a simulator, you get very disappointed. A simulator replaces reality, so you don't have to look at reality. I may even say you don't have to understand in detail. Well, that's not the case here. You have to understand everything in complete detail. So in order to implement this, of course, we need a research team that involves the computer science, mathematics, and somebody who can really push this. Applied science and engineering. I had great enjoyment in doing this. So one example of a model for which I guess we started with this 30 years ago, and we're still solving it, but we are at the end. We want to talk a little bit about the traveling waves that appear in this model. Please. Or whichever.
Good afternoon.
Oh, Ismail, I forgot to. Ledoin, I'm sorry.
Sorry, I'm going to have to connect my computer, my laptop. Sorry for all of these technical problems. We're almost done.
Nothing ever works.
Okay. I guess we're both seeing the same thing. Are we? Let me see here.
Okay.
Okay.
Pode fazer esse modelo, não tem problema.
Okay. So, as Dan told us, if we're trying to find traveling waves, we end up having to study a system of ODEs in our phase space. And so our problem is now based studying this system of ODs. And then we need a set of tools to study the phase space. And I'm gonna present to you some of them. So the first one, the essential, the first to program, is the Hugoniot locus. And I guess I didn't show the model here. This is the model I'm showing to you. The flux here is composed for those two equations, and the accumulation is the identity matrix. I say the identity function. And then, well, as you may already know, we want to make connections between two critical points of the system of ODs. Okay. Well, so first, what do we need to define the system of ODs? We need the first equilibrium, which is already on your screen, and we need the second equilibrium. Then we can define the shock speed, and then we can study the phase space. So here we do this in several ways. One of them is using this button. But now if you can see, there are some crosses. They're moving around. You can't see because I can't. Maybe a more interesting one is this button. See, you drag your second equilibrium, and then you see all the orbits going an epsilon away in the direction of the eigenvectors. This tells you somehow which equilibriums are connected to each other, and you can study like this. You may also see as many orbits as you want. And then you can do something like this. You see all of them. Perhaps it brings you a more understanding. But then, not all connections are found easily. These are actually saddle to node connections, which are the lax conditions. But we can have another type of connections, such as the transitional ones. And then, for example, if you start drawing your second equilibrium in the green region, you're going to see that at some point, the yellow curve and the right below the yellow curve, there's another curve, kind of blue. Yes, our screen is not doesn't let us see. See, there's a curve here. And then there's the yellow one right above. And as you drag the second equilibrium, you see that somehow those two curves, they meet at some point, or they coincide. And one of the problems is, how do we find such a curve, which is the transitional connection? Well, the one algorithm we know is it's like this. You draw a line. And then you start dragging your second equilibrium. And then notice we can define a kind of a vector connecting this point and this point. In this case, we just define a direction, for example, starting from the point which is the intersection of the segment with the yellow curve. And then we have a vector that goes into this direction. Now, if we keep dragging, we're going to see that at some point, such direction will change. Now you have a vector starting here and going to this direction, because the second curve, the second orbit, crosses the line here. So we see that as you drag the second equilibrium, those vectors change in direction. This allows us to make a kind of bisection algorithm in which we define positive is when the vector points to this way, and negative is when the vector points to this way. And we connect the 2 points which provide those vectors through the Hugoniot locus, and we try to find each of the Hugoniot locus point will provide us the connection from the Hugoniot locus origin to some point here, which will give us just the saddle to saddle connection. And then you do it. You provide, well, we know the connection is approximately here. Then we click here. And I'm not sure if you can see, but it was calculated, the connection starting here and meeting the other connection right here. So this point here is connected to this point via a saddle-to-saddle connection. Now, we might wonder, if we choose a different left state, will there be still a saddle-to-saddle connection if we perturbate the left state just a little bit? We can do this test. We just drag the left state. And put it here. Then you see that if we perturbate just a little bit the left state, we'll still have a saddle-to-saddle connection. But at some point, you see that the connection, the point which is connected through a saddle-to-saddle connection, it tends to the little square over there, which is the boundary between two different types of Hugoniot locus points, and you lose this connection. Now you have a second problem. How do we find the point which is the one that's going to provide the saddle to a saddle node connection? Because you'll have an orbit going out of the square, and this classifies a saddle-to-saddle node connection, because there is where one of the eigenvalues matches the shock speed. This is important because if you have a well-behaved problem, you'll have a certain boundary, which will tell you which region you can find saddle-to-saddle connections. Okay. Okay. I'm just going to show you one little thing. For this model, the yellow curve shows us approximately where all the left states can be chosen so that we will have a saddle-to-saddle connection. This is a bit expensive calculation, so you may find some discontinuities. We have some problems in the algorithm, but overall, it works fine. And this helps a lot understanding the conservation law. Well, I guess that's it. Thank you.
Thank you. How much time? No? 0? 5? Okay, so let's see if... Tá bom. Por favor, Luis Lozano, can you please show us what you've been doing? Aconteceu alguma coisa que não está grossa.
Okay, I can to show the utility to this program to study to viscous profile, and I understand to the solution. What is the effect? What is the effect of the capillarity pressure of the solution of the Riemann problem? But in many research with made a modeling the equations neglecting to the effect of the capillary pressure. But for example, the solution with you use the viscous profile in the use the identity matrix for is novel, and in my research I want to study when you change the viscosity matrix, the effect of the capillary pressure for the study of the Riemann problem. For this, the program that RP2 was implement of the Corey is the model of Corey, quadratic saturation of the oil, water, and gas. I can, for example, in this case, is when you use, I want to study of the transitional shocks. For example, in this place, I can to choose. The left state is the UL, and this point is over of the secondary bifurcation. In this case, the only possibility to have a saddle connection is in the same line, is in the green region here, and can to study for orbits and the study of flow for this region. Sorry, mouse. In this place, this is the flow for this point, and can you to see the orbits connecting in this point here? This point, this region is a red region. Have attractor in this place the same. Have 5 equilibriums, and in this place have a saddle. But what happened when you use other matrix? For example, a constant matrix but differ of the identity. For this, I want to plot other tool for this program is can you use to do at, for example, in this case, we have to orbit crossing in the middle of the line when you have transitional shock. In this case, for this matrix, for example, you lost connection saddles to saddle. That is an example when you use this program to study of the Riemann problem and the viscous profile for the 3-phase flow. Thanks.
Thank you. Let me go to the end. Está indo para trás. Well, you will be glad to have avoided all this theory. But anyway, what are Riemann problems for? One thing is they have the building block of the random choice method devised in 1966 by James Glim to find global solution of hyperbolic systems. That's one thing. The other is to have fun. But more seriously, let me see if I can. One important conclusion is that what we do is somewhat non-standard scientific computing and math. We use, or we are, a multidisciplinary research team with which we can get fast scientific insight. And this computer program is available to community so they can look at on their own screen rather than here. Okay, thank you.
Well, questions or remarks?
How about 5 image?
I don't think I'll, perhaps we can do 3 instead of 2, perhaps. You know, each dimension, you know how much it costs. Give me a Cray of the old times.
high dimension